quick break review. Right, so we kind of said a simple model of the brake system was we had some pivot, right? And that pivot basically was what our brake pedal pivoted about. And then we had the driver's foot, right? Applied some force to the foot here. And this was connected to a master cylinder, right? And we drew a little bit like this. And this went out to our tire and our brake rotor. And we had pads on both sides of this thing. And usually there's a piston on this side, but we'll just ignore it for now, as it doesn't really affect whether or not you're going to lock your brakes or not. And this went out to here. This is kind of the system we thought about, and this is filled with kind of incompressible hydraulic fluid. Okay. I should draw this better out here. And then we have a big master cylinder. There we go. Right, and so a couple of the important things that we cared about in this case were the length of the pedal, right? So that was down here to here, the length of the pedal. We cared about the length to the master cylinder. We cared about the area of the master cylinder. We cared about the area of the piston and the calipers, right? We cared about the distance from the center line of the tire to the radius of the pad, right? So we call that like kind of the center line of the pad. And we cared about the coefficient of friction between the pad and the rotor. So those are kind of the important things, right? And so we saw that the torque that we applied on the rotor, right, was equal to the force that you could put with your foot, and that got amplified by the length of the pedal over the length from the pivot to the master cylinder, right? And then it got amplified by the area of the caliper to the area of the master cylinder. So you had two amplifications, right? And those resulted, and since you had friction on both sides, you had to multiply by 2. So that was both sides of rotor. So we typically, remember, we said for like Baja and Formula, we use tandem master cylinders. So that also divided this by 2 down here. So we ended up having two things of 2 that ended up canceling. And this got multiplied by the coefficient of friction between the pad and the rotor, and then the radius of the pad, right? So everything to the left here is a force. Right? So this is all forces, right? And the other thing is the radius. So that was the torque on the rotor, and we compared that to the torque on the torque we needed on the tire to lock, right? And so the torque we need on the tire to lock was kind of the coefficient of friction of the tire to the ground, right, times the radius of the tire times the normal force, right? And the normal force we found was the weight divided by 2, because we have a left and right tire, divided by 2 times the wheelbase times, so we'll do this for the front. So this will be kind of front. And so we said this was C plus mu times the height of the CG, right? And that was if we drew kind of a little schematic of the car, and we had the CG here, right? And this is the height of the CG. This distance from here to here was B. This distance from here to here was C, right? And this distance from here to here was the wheelbase, right? So this term, so this is the normal force on the front, right? And it's got 2 components, right? It's got the static component here with the C, and it's got the weight shift component, right? And so as you're braking, that weight gets shifted to the front. So the kind of equivalent term here for the rear, right? So if it was the rear tire, everything's kind of the same except for it's losing the weight shift, losing the weight from the weight shift, and it's a B, right? Because it's the rear, you care about the distance here. So B minus mu height CG. And you might be kind of like, well, it's kind of weird. Why is for the front is it C, the distance from the rear? And you can just think about it because the CG went all the way over here to above the front tire. Then this C would cancel with this wheelbase, and it would just give it a factor of 1. And it would say the normal force on the tire statically is the weight over 2, which makes sense. If the CG is right over the front, all the way to the car is on the front, and you just divide it by 2 for the left and right tire. So typically we kind of wrote this N, kind of considered kind of like a factor of safety. It was the torque you applied on the rotor over the torque you needed on the tire to make it lock, right? And so we were hoping that the torque that we can get on the rotor is bigger than that. And so we basically put everything in all these terms in the top. So, right, we have the force of the foot, right? We have the length of the pedal over the length where it connects to the master cylinder, the area of the caliper piston over the area of the master cylinder. We had the coefficient of friction of the pad and the rotor, the radius of the pad, and then we just got to divide by everything here, right? So I'm going to put the force terms together. So we have weight, that 2 will come over the top, but it's okay. Wheelbase C plus mu height CG, right? And here we have mu of the tire and R of the tire. So it's kind of cool. It's kind of like if in fluids, you remember like these non-dimensional terms that affect it, right? You kind of have all these, you have basically 5 non-dimensional terms. 1, 2, 3, 4, 5. It's like, you need to apply more force on the foot than the normal force. You get an amplification, right? Basically, if you can get the length of the pedal bigger than the length of the master cylinder. Amplification if you get area of the piston on the caliper over the area of the master cylinder. If the friction's big on the pad, that's good, especially, and it's good you'll be more likely to like it to lock it if you're on ice, right? Like this coefficient of friction will go down. And the closer you can get the radius of this pad to the tire, the better, right? And so we said we wanted this, definitely greater than 1, but maybe greater than 1.5, to 2 or something. So that's what that was kind of the last thing we got to. This is an N, by the way. Last 2 for brakes, basically. And we talked about just kind of starting with the inner wheel diameter, right? So we started like 1 ID of the wheel to give you an estimate of the R to the pad, right? So if you get the radius to the pad, right? And so you'll have this, you can look these 2 up. And then you probably, to get R pad, you kind of assume to start, you probably want like LP over length of the master cylinder, right? To be, around 3. So that gives you these 2 terms. You can assume the force on the foot is maybe around 150 pounds. Right, and you can figure out everything about the bottom roughly, if you know just kind of some stuff about your car. So once you do that, it gives you an estimate of kind of the ratio of the area of the piston on the calipers to the area of the master cylinder. And you can start to look at the pressure of your hydraulic system, right, which is the force of the foot over 2 times the area of the master cylinder if you have a tandem setup, right? So you can start to figure out what kind of brake system you want. I mean, we usually use Willwood systems, right? And so once you know that, you can begin to package your brakes and your calipers, right? So here's your ID of your wheel. So, you need your calipers gonna have to go at some point between your rotor and the ID of your wheel. Right, so this would be like your rotor, here's your caliper, here would be like your pad. And so that tells you that you basically, The effective braking area will be in here on your pad, and then you connect to your hub on the inside, right? And you use the spokes at an angle so that they're more in tension and compression, right? So this is space right here, right? And that's just space to fit your caliper, which has to go up and around your rotor, right? Inside, and this is the ID of your wheel on the outside here, right? So the rest of your wheel's out here, right? And so you're having to fit everything inside of there. So then you can start to package everything. And then and we also kind of talked about how the coefficient of friction of your pad versus pressure looks something like this. So if you take too many cutouts out of your rotor, or you get your pads too small, basically your pressure will go up. The pressure associated with the force on your brake pads probably look something like this typically. Like this. And so, if you're not using all of that area, the pressure goes up, right? Between your pad and the rotor, right? Because this pressure here I'm talking about is the force on the rotor divided by the area of the pad, basically, right? So it's not the pressure on the hydraulic system; it's kind of the pressure between your pad. So that's why you actually want, higher coefficient of frictions happen at lower pressures. We see that with tires too, right? So you don't want to cut out too much. And we've seen that before. And then you can do thermal stuff. You can do FEA stuff. How thick do you need your rotor to be, right? All that jazz. So are there any kind of questions about the braking system from folks? Any of these terms, right? But I think this one's one of the more kind of like the results are more intuitive in my mind. It's like why, the kind of what things cause you to help you lock up the wheels. So we had that little special session last Saturday about kind of vehicle dynamics and roll, and I'm just going to mention some of the key points here. One, to try and get you to go watch it, and two, because some of them relate to our chassis design. Right, so we looked at kind of a half car model. Say your car looks like this. Let's say you got some tires. So let's say your tires, they pivot about some roll center here, right? Let's say they got some spring up to here. So this is kind of a model where this spring is the wheel stiffness. So this is a spring. So this is K wheel, this is K wheel. And we're looking, we could be looking either at the front or the rear right now, right? And this is the roll center. This might be your CG. This distance from here to here is the height of your roll moment. The distance from here to here is the height of the roll center, right? From the ground. And keep in mind the stiffness of the wheel is kind of like, how much force is applied on that whole wheel assembly, how much does it travel up and down, right? And so this thing in a roll, you imagine, right? So this thing will kind of roll like this. Right, so when it rolls some angle here, between here and here, some angle phi, let's say. And so phi is the roll of the car, right? And so you imagine this whole thing is kind of rolling, and this would be like a sharp left-hand turn, the car's rolling to the outside, right? And this, the right shock is compressing, the left shock is extending, basically. So we define something called K phi, and we do it for the front and the rear. So the I could be F for front or R for rear, right? And this is the roll stiffness. Right? And this was basically how much moment do you apply about the roll center, divided by the amount of roll that you get, phi. So this is roll you get, right? So it's basically like, it's kind of like a K for a spring is F over X, but it's for rotation, right? So you imagine instead of a force, it's a moment. Instead of a displacement, it's a rotation, right? And you can see this car is kind of rotating some distance phi to the right. And just how stiff is it? How much, you know, so the higher this number, you have to apply more moment about the roll center to get the car to roll. And so we did a little bit of analysis last time to find that K5I is equal to 1/2 the wheel stiffness of the front. Usually you do this for the front or the rear, right? Times the track width. So TW is track width squared. And this will give you an answer in let's say here, some moment per radian. Right, so this is going to give you per radian, right? And you do it in the front, and you can do it in the rear. So, and then we remembered last time that K of the wheel, right, is, we relate that usually to a natural frequency. So usually we use a natural frequency just to start us getting some of the ballpark. And this was omega n. And usually the rear is, right, it's a little bit higher, maybe like 10% higher than the front. Times 2 times pi squared times the sprung mass of either in the front or the rear, basically. So that's how usually we got the wheel stiffness to start. All right, so we cared about the roll stiffness, but we also cared about this thing we called R roll, which was the roll rate or roll flexibility. And this describes how much does the car roll. So like phi, how much does the car roll per lateral acceleration? Right. So it says if you took like a 2g turn, how many degrees or radians does the car roll, basically? So that's what this number tells you. And so we found our roll, the roll rate, right? And last time we said, okay, well, it was kind of what is causing this roll, right? And so that was the kind of mass divided by, in this case, so we're doing this per acceleration, so we divide by acceleration. So mass times acceleration times the height of the roll moment, right? And this was the height of the CG minus the height of the roll axes. So R axes above CG. So this was kind of weird in that in a car, you have a roll axis probably a little higher in the rear than you do in the front. So your car rolls about, so this is your height of the roll center in the rear, height of the roll center in the front. So this is your roll axes. So your car rolls about this roll axis connecting your front, and your CG might be here. So the height of the roll moment is like right here. So for the whole car, that's your height of your roll moment, actually. It's actually like, so you kind of have to, you imagine you have to know something about the front roll center, the rear roll center, and you have to draw a line between them and then get this distance. It's not too hard to do mathematically, it's just the line, right? So, but that's how you find this height of the roll moment for the whole car. And then you just divide that by the stiffness, right? So you have K phi of the front, plus you have a term for the rear, right? And you have actually minus this weight times height of the roll moment. And that's because if you see up here, so I'll box this equation just so you can, that. So you see here, actually, as it rolls, this CG actually rolls too, which actually now the weight of the car actually helps it roll more. So that's why you get this little term. It doesn't, if you neglected it, it doesn't play a huge role typically, but it but it's there, right? And so some other things to note is if you actually divide this by the g, like 32.2 feet per second squared, then when you want to figure out your roll, you have to multiply it by an acceleration in feet per second squared. If you just don't divide by the g, and you know this g remains in the denominator, you can just multiply it by 2 for a 2g turn. So you can either do it like per g, or you can do it per feet per second. So, because this is going to give you units, right, of like radians per either feet per second squared or g, which would be like 32 feet per second squared. So just, right. So keep that in mind. If you do some, you should be getting a few degrees probably. So if you're not getting a few degrees, you know something's wrong. So then what we kind of cared about, actually maybe some of the most, was what was called the lateral load transfer distribution. How much load is being transferred in the front versus in the rear? Right, so this was LLTD, is what most people call it. What's the LLTD? And so we compare, and so this is usually front divided by rear, because you want close to the same load transfer. So if you have more load transfer in the rear, you're gonna get oversteer essentially, and if you have more load transfer in the front, you're gonna get understeer. So I'll go into that in a little more detail, but so this LLTD, so the load transfer in the front we found was the roll stiffness in the front times the total roll resistance. So this is for the whole car. It's not for front and rear. This is for whole car. There's no kind of, you don't really define a roll rate for front and rear. It's for the whole car. But this other term is for the front. So this, when you multiply these two together, you kind of think about it, you get roll per acceleration. This term up here is moment per roll. So what that gives you is moment per acceleration, right? So it's kind of like the moment is what's causing the weight transfer. So you have K phi F times R roll plus you have the weight of the front divided by G, kind of give you the height of the roll center of the front, right? So that's the height of the roll center. So this term, and you have the same terms for the rear, K phi of the rear times the roll rate for the whole car plus the weight in the rear divided by G times the height of the roll center in the rear. So this term is kind of the weight transfer through the suspension links. And this term is going to be equal to the weight transfer through the springs. So the way you can kind of see that is, so like for example, if you designed your roll center all the way right here at the CG, then your car doesn't roll at R because you have no roll moment. So your R roll is 0. And so these terms basically go to 0. And so it's like, how is the weight being transferred? Well, in that case, the weight is basically being transferred directly through this link, right? The link between the suspension, right? It's being transferred through your lower control arm and upper control arm. And so you usually design this, you want your LLTD desired. You usually design it for a little under 1, about 0.85, because stuff that you don't take into account usually causes you to understeer. So like, there's compliance in all your links, the camber of your tires. Usually things cause understeer. So we err on the side of making the car oversteer. right? So like an LLTD of less than 1 is kind of an oversteer, because that means you have more weight transfer in the rear. And LLTD greater than 1 is understeer, because you have more weight shift in the front, right? And so this, and you go a little under 1. And so what you're typically going to find here is you're going to get like 0.5, 0.6. And so you need to make your rear a little bit, you need to make your front a little bit stiffer. You need to bring this up. So what you typically do is you add a term like, let's see here, K phi of the anti-roll bar, basically, right? So you add this roll stiffness of your anti-roll bar times R roll, right? So this adds stiffness from an anti-roll bar. And you solve for this by putting in your LLTD desired, right? So you imagine if this one was actually 0.5 before, and you switch that for 0.85, it needs to be bigger. So what causes it to be bigger, you'd have to calculate is this term, basically. And so that's going to give you how stiff should your anti-roll bar be, right? So if you want to, and then we'd have to talk more about designing an anti-roll bar, but there's plenty of stuff out there. But this could tell you, and it's nice to have at least one anti-roll bar, because then you want to find a way to adjust your lateral load transfer. So you're going to be slightly oversteering or understeering, so you want to be able to adjust it. You can obviously adjust it by adjusting the stiffness of your shocks, right? Because we see this, so if you can adjust your stiffness of your shocks, you can adjust your tire pressures, you can do a lot of stuff, but usually you'll see like on a car will have several spots that the anti-roll bar can be connected to. And the reason for that is so that you can adjust the stiffness of the anti-roll bar to tune this in so you're getting neutral steer, basically. So that's a little bit kind of the basics about kind of the roll dynamics and how you go. We were doing a lot of linear systems before, but how do you consider roll, which is especially big for formula. But I think Baja, interestingly enough, I think always makes this. They want a crazy amount of oversteer because they have a fixed rear axle, so they have trouble steering. So if they have a ton of oversteer, they can kind of drift. So they artificially make their rear super stiff with super stiff springs, but in actuality, it makes the harder to drive over the bumps. So I think ideally we use an anti-roll bar, and like rather than make our rear springs so crazy stiff. I think it also causes the forces in the rear to be larger than they need to be. So I think we also break things more likely because of it. That's just total speculation.
I have a question. That anti-roll bar, that's just for the front? Like, so if you did the rear, you'd put it on the bottom?
Yeah, exactly. So for example, if you found this was 1, like you found, oh man, we need to make it stiffer in the rear to get down to this, then you do the same thing, but you'd add one in the bottom. Okay. Or you should also be checking your like, also be checking your phi max. Like what's the max amount of roll you're going to get, which would be like your R roll times your max lateral acceleration, right? Like, and then you basically, what you do is you get delta, let's just say max tire travel, right, is going to be equal to your phi max times your twack width over 2. So you should also be seeing, it could be the case that your car setup is just way too soft. And so you're getting way too much roll at high speed turns, and you're traveling either too much, or maybe you can also relate your max tire travel, right, to your max suspension travel. Like you might be using up all of your suspension travel and bottoming out, right? And so in that case, you have to make both the front and rear stiffer. So if that's the case, you might add them to the front and rear to make this whole part stiffer, and then you to make the whole car stiffer, and then you can adjust them in to get the desired value of this. Keep in mind when you change this, you should actually, it also will affect your roll rate. So you should actually iterate on this process. You should figure out what this is, then add this term, just the K5 part, into here, recalculate R roll, and recalculate your LTV again. Because you see, this R roll is also a function of this term. So this, when you change this term, it'll actually change R roll too. So you can't, but usually if you do this one iteration, it's pretty close even. So that's a little bit of the last bit there. So I think we're ready now to talk a little bit about the chassis, or otherwise known as the frame, or I think Baja rulebook calls it the roll cage. So of course this is kind of, we usually do a tube frame. Of course, there's monocoques and other stuff these days, but I think for us, probably we're going to be doing a tube frame for at least the next 3 to 4 years. I don't think there's that much to gain from the, and then I don't know if we have the resources to start doing the monocoque quite yet. We're not even doing aero yet. But so I think first rule of chassis is pass all the rules. So this is the one subsection that has the most rules associated with it. The nice part about it, if you pass the rules, it'll typically help you do the other things. But I find like too often with our teams, like people just don't even know the rules. It's like, sometimes I feel like I'm like coaching a basketball team, and like one half of the team is arguing we should shoot the 4-point field goals, and the other half of the team's arguing we should shoot the 1-pointers, and then it's like, and then we look, we spend like a week or two arguing about which one's a better strategy, and then we look in the rules and realize like, oh, that wasn't even like that's not even something in the rules, right? So it's like
our meeting.
It's like, this is a competition, right? And the competition has a set of rules about it, and so like operating within those parameters is pretty key. So knowing them is pretty key. I know they're daunting. I mean, the hard part about this one is like there's so many freaking rules, but I think to be competitive, we really need to bite down and figure out a way. Maybe someone can find a way to have some sort of competition or something to see who knows the rules the best on the team. Find some way to get us to actually read the rules, because I think it also, if you don't know what the rules are, it's hard to operate on the edge of the rules, right? So it basically means we're not really being as competitive as we could be. But anyways, so that's a side point about reading the rules. I think luckily enough, Leo knows the rules pretty well. So
I just learned mine too. So
okay, nice. So I think both we've been lucky in that. I think our chassis people know the rules better than anybody. So we're lucky in that regard.
Thanks, Leo.
So I mean, the first thing is it protects the driver. I mean, that's why they care so much about it, right? I mean, it's like the only thing saving the driver in a rollover or running into something. All right, and then 3, it provides mounting for all the other subsystems. Right, so I mean, that's why this person almost has to be kind of somewhat of a system level engineer, because, well, maybe not, I don't know, maybe we shouldn't call them a system engineer, but they would have to work a lot on integration, let's say, right? So, so these are kind of these are some of the main points here. So let's look at a couple of the, so let's look at some of the Baja and formula frames here. So let's look at the Baja one first. All right, so this is kind of so Baja, interestingly enough, they have 2 kind of bracing options, one with extra bracing in the front and another with extra bracing in the rear. We still kind of run the engine in the rear, so typically we need extra space back there anyway, so we typically run the front bracing. in this drawing in our handbook, anything that's kind of a shade of blue, kind of dark blue, blue or gray, is primary tubing. So you can see this nose, this down and up to the overhead member, and down in here, this is all what's called primary tubing. So that's how Baja kind of does it, is they take the, and they say they have primary and they have secondary. So, and then everything else are secondary that's required. And then you can, if you add in any other tubing not associated with this, it can kind of be whatever you want. So in Baja, their primary tubing has to be equivalent to a 1-inch outer diameter and a 1/8 wall thickness, basically, right? And at minimum, it has to have at least a minimum of a 1/16 wall thickness. You can't go any thinner than that. And then for their secondary members, it has to be a minimum wall thickness of a little over a 32nd, and it has to be at least 1 inch, right? So this one you can't do equivalents, but the primary you can. And the stuff you have to care about, the metrics for Baja are bending strength and bending stiffness. But buckling and bending stiffness actually seem to have the same metric. So those are the ones we'll care about for them. And they have these two values they give for the yield strength for steel and the Young's modulus for the steel. Okay, so let's look at formula. So formula frame, here's like basically the simplest frame I could think to make with formula, basically, that would pass the rules. And so you can see how they do it. And so they have the front bulkhead, that's this green. B is the bulkhead support, right? So it's this purple stuff that comes from the front bulkhead to the roll hoop. So the C, right, is the front hoop. D is the front hoop bracing, right? If it's forward braced. So rear brace would mean you'd brace it backwards. We typically brace it forward. You have the side impact structure, right? You need 3 tubes here. Then you have your main hoop, right? You have your shoulder harness, and then you have your main hoop bracing, and then you have your main hoop bracing support, basically, down here. And you can see what they have different sizes. They have a size A, B, C, D for their different tubing sizes. And here's like A, B, C, and D. And so you can use, for example, like we do, we just use this, I think, tubing basically for A, B, C, D. But you can also check to see if it meets the minimum requirement for each of these. This minimum area moment of inertia, minimum cross-sectional area, minimum outside diameter, and minimum wall thickness, right? And if you want to use a tubing that does not meet all 4 of these, you need to check the equivalence of both tension and compression, the bending strength, the bending stiffness, the buckling strength, and the bending energy absorbed. So and they give you these values. So they actually the yield strength, surprisingly enough, is quite a bit lower than what they expect for Baja. And then here, so let's talk about a little bit of let's talk a little bit about how you can check this equivalence on these tubings. Right. All right. So tubing equivalence. Right. So the first thing, let's talk about if it's equivalent in tension and compression. So the stress from tension and compression, right? So you take a tube, pull on it, some force F, has some cross-sectional area AC. The stress is just the force over the cross-sectional area. And the factor of safety, whether it's going to break or not, is equal to the yield stress over this stress that you're applying to it, sigma here, right? And so if this gets less than 1, then it's going to break, right? Because that basically means that this got greater than the yield stress, which you don't want because the yield is kind of our failure criteria in this case. So if we replace this, we get SY times area of the cross section over the force. And basically we make a metric to say how strong is it. So the metric in this case should be the product of the factor of safety and that force. So if your tube can get the higher factor of safety for the same force, so basically a bigger number here, that means it's better than this tube in tension and compression, right? So this is kind of the key metric, the yield stress times the cross-sectional area. So if you have a bigger yield stress, you have a higher factor of safety for the same force than like, you know, so let's say if like tube 1, you know, has a greater value of this metric compared to tube 2, that means that for the same force, it has a greater N. So let's say these two happen to be equal. Its N is greater than tube 2, right? So you can use this basically to say, is tube 1 better than tube 2? Is the yield stress times the cross-sectional area for tube 1 greater than the yield stress times the cross-sectional area of tube 2, right? Which basically means if you can get a tube with a higher yield stress, you can decrease the cross-sectional area, right? So this is the metric we're going to compare tubes to see if they're equivalent on tension and compression. Do they have a higher product of yield times cross-sectional area, right? And that makes sense that a tube gets stronger in tension and compression if it has a higher yield stress and if it has a higher area. All right, let's look at bending strength. So for bending strength, the stress in bending is equal to the moment on the tube times the distance from the neutral axis C, right, over I. So we're just going to do the same thing. All right, factor of safety is the yield stress over sigma. This is kind of our failure criteria. It's SY if it hits the yield stress. And so basically what we'll have is we'll have SY. We're going to have MC and I here. And then we're going to make a metric. Right, so I'm kind of making a metric of everything that's kind of independent of the tube, right? So my metric is going to be equal to the moment times the factor of safety. That's not really dependent on the tube. And everything that's kind of dependent on the tube is SYI over C, right? So this is usually like the diameter over 2, right? That's the distance from the neutral axis, the axis that doesn't see any stress or any yielding, or not yielding, any strain. And then I is the second moment of area, which for a tube is just pi over 64 d outer to the fourth minus d of the inner diameter to the fourth. So I is equal to, right? And so again, we're going to compare, does this tube, and this is d outer, does this tube have a greater SYI over C as kind of our metric for is it stronger or weaker, basically? All right. And then we have bending strength or bending stiffness. So stiffness is different than strength because it looks at how much does it deflect, right? So for example, the deflection of a beam of the end of a beam, this is fixed, and you apply a force, right? It's going to be equal to the moment. So that moment is going to be F times L. Right? So the moment at the base is F times L. So it'll be the moment times length squared over 3EI. Or you could say this is FL cubed. Maybe even FL cubed is better. FL cubed. But we typically will, so for our metric here, what we basically do is we say for the same delta F L cubed, and we'll also multiply by 3 delta. This is going to be, I'm going to invert this. So I'm just going to invert it. I'm going to move in this case, I'm going to move the delta over. I'm going to move, so I'm going to get, let's see here, I'm going to get FL cubed over 3 delta, which is equal to EI. It's kind of our metric. And so basically what you can see is the tube is, if this metric is higher, the tube will basically deflect less. So if you apply so let's say if this metric is high and this force is constant, that means this delta is smaller. So the higher this metric, the lower the deflection. Right? For an equivalent tube, force on the tube and equivalent length, right? Since we're we're not changing the tube's lengths, we're just changing their cross section, right? So that gives us EI as our criteria for bending stiffness. So, and then we have buckling strength. So if you have a beam, it depends on it depends on if it's like pinned or fixed, but we typically just look at kind of the two, we look at the case where the kind of this factor is 1. Let me see, I forget what case is that. I think it's probably pinned. K is 1 is both ends pinned, yeah. So we do the kind of both ends pinned case because we really just care about the cross section. We're not like changing the way it's pinned. And so this will fail in buckling, which basically means that it'll kind of like, actually the side will kind of blow out, right? Before anything sees the yield stress, right? And so the kind of the critical force for buckling is pi squared EI over K times the length squared. And so we usually just put in this factor this K factor is just for the end conditions, whether it's fixed or pinned, end condition factor. We just assume it's 1. And so basically in this case, we make a metric, and our metric is this force times KL squared divided by pi squared. So we just put all the constants and stuff in here. And so the higher this value is, the less likely it is to buckle. And this is equal to EI. So you see we actually get the same, it's the same actually, so you don't need to do 2 actually. Buckling and bending actually turn out to be the same. So basically the higher this metric, the higher force to break it, which is good, right? So if you find a tube that is higher or equivalent in this metric for the 2 tubes, so the product of the Young's modulus, kind of how stiff the tube is, times its second moment of area, it's good for buckling and bending strength. For bending strength, right, you need high second moment of area times yield stress, right, divided by that distance to the neutral axis, and then yield stress. And so, I mean, it makes sense that the criteria for like buckling and for bending, which have to deal with kind of things having to deform, that it's that they are related to the Young's modulus, and the stuff about whether they're going to yield are related to the yield stress. So the last one is about bending energy. And they don't actually say it has to be bending energy, but I think that one makes the most sense. It's basically like in an impact, right? Let's say you have some tube, right? Like this is maybe like your side impact structure, and you hit some huge force, right, on the side. They want it to be able to, and you have to apply some force over some distance before the thing ruptures, right? So some distance d. And that's the energy that is dissipated by this tube before breaking. So this energy times the force that it takes to on the tube times the distance, right? And it's actually the integral of this, because you might see like the force versus distance curve in this case. It might look like something like this until it ruptures, and here's where it breaks, right? So you keep pressing it harder and harder, it keeps going further and further, and then it ruptures. And so the area under this curve is E, right? So for this pin beam, basically, we know that the stress at the ends here, where it's going to break, is equal to the force times the length times distance to the neutral axis times EI. So we can just look that up in a table. And we relate this to the ultimate tensile strength in this case, because we care about it. We don't, if we take a hit like this, we just want to see how much it can take before it actually gets buckled in, basically. And so we know that this is the force we're going to apply, basically. So our force is going to be the ultimate tensile strength times 8 times I over its length times C. And then the amount that it deflects, this distance d, before it breaks, will be this F length cubed over 192 EI. So we basically, to get the energy, we see that the deflection is linear. So the deflection is linear to the force. So that means it's a straight line. So if we basically multiply this value, kind of delta, this d, times this F max, the area is just equal to F max times delta over 2. So we really just have to multiply these two. So we have force, and now we have delta, so the energy is just force times delta over 2. And the force times delta over 2, so I'm just going to, basically the issue is I have this force twice. So I have 8 SUTI over LC, and this is squared, because inside the delta there's also an F. And then I have a length cubed over 192 EI. And so this is going to give me E. So I'm going to have this 8 squared, which is 64. I forgot this 2 down here. 2 times 2. And then I'm going to have this ultimate tensile strength squared. I have 2 I's on top, right? I have 2 I's on top, and so, but canceled by 1 here, so I'll get 1 I here. I have 2 L's on, see how it does that. 2 L's on bottom, and then 1 L here, so I'll get another L on top. And then I'm going to get 2 C's on bottom, so I'm going to get a C squared. I'm going to get 2 times 192, and then I'm going to get an E on the bottom, right? And so this will kind of reduce down to this must be like a 6 or something. That's 2 times 3. Oh yeah, so this should be SUT squared times I times L over 6 C squared E. And so for my metric, in this case, I want the most energy dissipated, right? This E is Young's modulus. And this is energy, so I should put energy. So let's just do energy. So I'm going to want it to be the energy. I'll bring the 6 over here, and then I'll divide by the length, because the length will be the length will be the same no matter if you change the cross section. So this is the ultimate tensile strength squared times I over EC squared. So this is kind of an interesting metric to see how much energy can you dissipate, and it's more related almost to I over C squared, which is interesting because in bending it was just an I over C kind of. So this is kind of the metric. And they have to, right? And so all of these C's are like d outer over 2. All of these second moments of areas are pi over 64. times d outer to the fourth minus d inner to the fourth, right? And then they have yield stresses, they have ultimate tensile strengths, and they have Young's modulus that they give you to compare to. So all we're doing basically is we're saying, okay, can we find a tube that's lighter maybe, but that is stronger in bending or can take more bending energy, is stronger in buckling, is stiffer in bending, is stronger in bending, and is stronger in tension and compression. Baja, you only have 2 metrics. So what I basically did is I made a little tube calculator for myself. I basically, hopefully folks, you guys can see my screen, right?
Yes.
Yeah.
So I put in the outer diameter in inches, it calculates outer diameter in millimeters. I put in the inner diameter, calculates the thickness in millimeters. I put in the length and all these properties, and it calculates all this stuff. And it was funny, I was kind of looking at all of it and I was thinking like, well, this is gonna be really annoying just to put this in for a bunch of tubes. So what I decided to do instead was, what I ended up doing is I put in like the reference geometry. So for this is weight comparison of formula with A tubing basically. And I put in the outer diameter, I put in the inner diameter, right? And then I solved for what's the cross-sectional area. I calculated for the second moment of area. I did I divided by C, right? Second moment of area divided by the diameter over 2 and divided by this. And I said, what are the properties of this? So I just put in the reference properties and I put in the density per inch basically. So this is basically going to be the density times the cross section. And then I kind of asked myself, so if I get a different tube, and I fix the outer diameter of that other tube and I fix the material properties, how big does the inner diameter, how big can I make the inner diameter? So like how thin of a wall tubing can I get? So it's just as strong in tension, basically. I want it, so this is kind of the inner diameter of a tube that's just as strong in tension as this. I did the same thing for buckling, bending, and energy dissipation, right? Kind of those 4 things, since we saw that this buckling and strength and bending strength. And I got these plots. So basically right here on the horizontal scale is the outer diameter. And on the vertical scale, I plotted the weight of the smallest tube that meets that criteria, right? And so black here, this is the weight of the reference tube. It weighs about 0.08 pounds for every inch length you use. So you'll notice immediately so this is the standard tube right here at 1 inch. Immediately you're restricted by buckling strength, right? So even you'll notice, so let's look at the tension. So because I'm using 4130 chromoly, which has a higher yield stress, I immediately can use, for tension, I can jump down to a lot thinner wall tube, right? But the buckling strength does not allow me to jump down because then I'll drop under what's limited by buckling strength. So, I mean, as far as I can tell, the energy dissipation and the, because the ultimate tensile strength is much higher, you're not worried about really energy and you're not even worried about bending strength because you have these other properties. So if you want to, for formula, it looks like to me, if you go bigger along the buckling strength, if you go bigger in diameter, you can go smaller in wall thickness for the same buckling and bending stiffness. So for me, it seems like instead of we're operating here with regular steel, we could go down to a weight that's 0.05, it looks like roughly. So it's about 60% of the original weight. But there's no point of getting any bigger because in that point, we're now limited by the tension, strength and tension, basically. So basically, if I was like, what's the lightest chromoly tube we could use? We could go about 30% lighter, but we would, and this is only for the A tubing, right? You'd have to do this for the B and C tubing, but you could go about 30% lighter and you could get down to a 50 thou wall thickness. So here I basically plotted the lightest possible tubing, basically, with the lightest possible tubing that meets all of these rules, right? So initially it's all the way up here, comes down around past the reference. So you don't want to go any smaller in outer diameter. So you go bigger in outer diameter, and that allows you to shrink the wall thickness. So you see your wall thickness can go down. And so the point where I think you just kind of operate around here, your wall thickness is maybe around 50, 60 thou. But that's just to get your tube a little bit lighter. If we go over here to Baja, that's formula B. So Baja is a little bit different. Baja, interesting, they don't care about tension. They also don't care about energy dissipation, but they also have, this should say weight at minimum tube thickness. But you cannot go below a 62 thou tube on your primary. So this is basically the weight of a tube with 62 thou. So Baja is limited by blue, green, and this orange. So what I basically see for Baja, this line does not matter for Baja, and this line does not matter for Baja. So what I basically see is Baja should travel down to about 1 1/4, and that can get them also about 20 to 30% lighter on their tubing. I think that's probably about what we use. So Baja's has a little minimum down here, actually. If you use the 62 thou wall thickness, which is like this value right here, it looks like maybe about 1.2. So I've only done this kind of course. I did this for outer diameters of 1.2, 1.3. So it might get a little finer if you, but of course you can't get any, you could probably, I'm not sure if you can even get a 1.2 outer diameter tube. You might be able to only get a 1 1/4. So you could go 1 1/4 60 thou, and you'll be lighter than you are at 1 inch, but not by that much.
Turn it.
Yeah. So that was chromoly steel. It's actually interesting. If you do this this actually isn't all that different. If you do it, for Baja, if we just use regular steel, the 1020, we can actually get down to about, so you see everything goes through this point because the material properties aren't different. And we could ignore this yellow one because there's no energy dissipation requirement for Baja. But you could actually come down here into this weight, about 0.065 with regular steel. And that's not all that different from the chromoly. So it's interesting, the chromoly for Baja doesn't make it that much stronger, or that much lighter. But keep in mind, you might be able to find chromoly with higher specs than these. I don't know, I kind of just grabbed these specs from online, but you'll have to get a certified material. So it depends also what certified material specs you can get. So if you get stuff with a higher yield strength than this, then you could even make stuff a little lighter. So that's kind of how you game. And I mean, it was interesting with formula because people had always been saying like, oh, you can't, with formula, because of the tension, because of the tension and the buckling, all these requirements, you can't actually get much lighter. It seems to me you could get 20 to 30% lighter. You'd have to use chromoly, which is more expensive, harder to machine. It's not any stiffer. Keep in mind, chromoly steel is not any stiffer. It's not going to help with your torsional rigidity. All it can do is help make your car a little bit lighter. So I don't know if that's worth it or not, but you might, I don't know, frame that's 20% lighter is, I don't know, 5-10 pounds. So I don't know if it's worth the hassle for 5-10 pounds, but just something to think about in the future. And you could, at least you want to be able to tell the judges that you thought, they're going to ask you, why'd you pick that tubing, right? So you should at least have some kind of, not just, oh, we were lazy, but like, we considered the different options and we weren't able to save that much weight based on the rules, So I think even if you don't act on it, it's still cool to do analysis to say, we knew we could do this, but we decided that, the cost and ease of manufacturing was more important than the extra 5 pounds, right? I mean, there's a lot of ways we could save 5 pounds on the car.
Chris?
Yeah?
You had a chart up here where it showed the a formula chassis, like different colored tubes, and
Yeah.
then it showed what the different over here was showing. Maybe I was looking at something else. It showed here where the wall thickness of some of the tubes are like half.
These ones?
I'm not sure if this is the same one. Let's see here. Okay, yeah, right. A tube is 95 thousandths wall. A D tube is 47. So that's half the weight.
Yeah. But keep in mind, you can only, so if you look at this chart, you can only use the D tube for the bent upper side impact member. So you can't actually use the D tube. So you see down here, you don't have an option between A, B, C, D. This chart down here basically says for the front hoop, you have to use A.
Yeah,
So
right here.
So they know these are not equivalent, but you basically, they specify what's the minimum requirement for each tube in the chassis. And you'll see some, like the main hoop, you cannot even use an alternative tube.
Right.
The main hoop and the main hoop bracing, you can't even do this for. You have to use something that meets these requirements.
There's a couple of tubes that they actually check. The main hoop is one of them.
Yeah.
They have a what is it, ultrasound of a micrometer.
Yeah, I think so. And they put it up against it. The
Yeah.
ones I've seen, they kind of just walk around and they'll put it on some different tubes around it. Especially Baja, since they'll go around and put it on all the primary and all the secondary. So I don't think, but yeah, they definitely probably check the main stuff they care about, like probably this front bulkhead. They probably do a couple of the side impact structures. They probably do the main roll hoop for a rollover, right?
The side impact structures are what
Side impact structures E, that's tube size B.
so
When
that's
they did it,
about a third.
when they did it, they pretty much did, yeah, all the ones you said, like whatever's exposed, like I guess
Yeah.
the main one. They didn't touch the suspension or anything.
I
And
guess
your suspension has no tube requirement. I mean, you can make
Yeah,
your
that's
suspension out of aluminum foil if you wanted to.
okay.
I think the main benefit to keeping it all the same tube, that 95 thousandths, you can't screw up.
Yeah.
You buy enough of it to build a car and a half, and when you're done, you have some tubing left over, and you got a complete chassis that's passes tech.
Yeah. But you are using significantly heavier tubing. I think Leo, you might correct me. You probably used some of this size B and size C, didn't you? Or no, you used all A on everything.
On what parts? The A I just use it for the hoops.
Got you. So you use mostly B then, or B and C. Like for the front bulkhead support, did you use a different size tube?
That was a B. It was a
Okay.
0.065.
Yeah. So you could go a little thick. You could go a little thinner on some stuff, but you're right. It's like, is it really worth ordering a whole another set of tube and potentially messing up and not passing, right? So it's also, I think Bill, I mean, there is, I think at some level you have to decide, is the weight savings worth it in some cases?
Or the geometry, you could look at something else.
If you had a metal rack where you could keep everything separated, it would be okay. Just make sure who's digging out what for what purpose.
Yeah. Yeah, we're known for our organization and on our SA team, so that's good.
Well, we got. I don't think it's really us.
Inability to ever make mistakes.
Facilities are a bigger part of the problem that people use it, I think. Just not enough room.
No, I got that makes sense.
a
All right, so another really important part about the frame. So connections to the frame. So that's just the tubing, right? We haven't even talked about anything really important yet. Connections to the frame.
Getting wound up.
So right, all connections should be to triangulated nodes. I mean, so let's look at let's look at one of our example tubes, right? So let's say we have a case where we hook up to one of our tubes, right? And let's put all of our tubes maybe like just 12 inches long. Let's say what happens when we hook it up and we put a force just like a triangulated. The nice part about triangulated nodes is it puts stuff in tension and compression, right? Non-triangulated stuff, it puts it in bending, right? So let's look at the relative strength and the relative stiffness of putting something at a tube in compression versus putting it in bending. So, and we'll even not even do the worst case scenario bending. Let's do the one where we're putting it like in a half length, or like halfway on a fixed tube, basically, right? Versus the force here. All right, so let's compare. So, and we'll do this just for the primary formula tubing. So in this case, the sigma is F over A, and let's put in like a normal, a pretty common force, like, I don't know, 500 pounds. That's probably like the worst case scenario, some load coming in from the tire. That's like pretty high. Maybe let's even do 100 pounds. 100 pounds. Right, so the factor of, so sigma is going to be equal to the force 100 over the area of our primary tubing is 0.27 inches squared, and the factor of, well, I guess we don't have to worry about the factor of safety. So what's the stress in this case? Maybe it looks like around 400 psi. And let's look at the deflection. So sigma is also equal to E epsilon, right? And so an epsilon is strain, which equals E change in length over length. So we're going to basically have change in length is equal to sigma, is equal to sigma, right, times the length over E. Right, so this is about 400 psi times 12 inches divided by about 30 mpsi. This is roughly the Young's modulus for steel. So you got 400 times 12 divided by 30 e to the 6th. So this is 0.1 thousandths of an inch. So move some, but only a thousandth of an inch, right? And we're at 400 psi. So that's, let's look at what's the case though when we put the tube in bending. Let's see. Let's make that quick comparison. So the stress in this case is equal to the force times the length over C over 8I. So for our case, so we have 100 pounds force times 12 inches over 8, and then C times for the C over I for formula A tubing. Let's see, so 0.056 times 0.056 inches cubed. So that's going to give us 100 times 12 divided by 8 times 0.056. This gives us sigma is equal to 2,679 psi, which is equal to 7 times tension / compression. So basically, if you decide to mount your tube in the middle, put a mount in the middle of your frame, then it's going to be 7 times weaker, right? Just because you chose to mount it out there. Let's look about how stiff it is. So the deflection that you're going to get, so deflection is going to be force times length cubed over 192 EI. So that's going to be 100 pounds force times 12 inches cubed over 192 times 30 mega psi times the I of formula primary is 0.028. Let's see what this is. So this is 100 times 12 cubed divided by 192 times 30 e to the 6 times 0.028. It's 1/1000th of an inch. Or 10 times higher than tension and compression. Right? So this is why it's so important, one, to triangulate things, to keep things from being in bending, but also two, to mount everything at a node, basically. So I mean, one, you'll notice that's why, like the formula frame, right, the requirements, you'll notice that's why they care so much about things being triangulated. One, they're strong because things are in tension and compression. And that's why you'll see so many teams to mount everything at a node, right? And especially like this node and this node down here, these are good because they have members that go across. Like this node is not as strong because it's basically 4 tubes in bending, right? And so this tube can go in and out of the page pretty easily. So connecting to tubes with crosses on them is really nice. Or like this front tube, it should actually have a cross across the front. That'll make this tube strong. Or it has a cross along the bottom, so that's good. So you want stuff that's not only triangulated, but you also want, I mean, if anything, it should be a tetrahedral. A tetrahedra is even better than triangulated. So if you can actually make tetrahedra, that's even better. But tying into these nodes is most important. Baja, the frame's a little bit more open. They allow some squares, which is bad because the squares can kind of deform. But like, for example, see this square face, like that's probably not that good. I mean, but you see, that's why they triangulate this back basically right here. They triangulate this back structure. So that's why they have a triangle here and a triangle here. And that creates this kind of hard pocket basically right here that they put everything else on the frame across. But you should check. So the most common, so if I had to make a frame, I first, so like relative strength and stiffness. Right, so first I would make tetrahedra, right, and I'd put forces at the nodes on a tetrahedra. The next I would do triangles, and I would put a force in the plane of the triangle. You know, this will cause things to kind of buckle pretty easily, but you could do a force on a tube. And then the last thing I would do would be to put forces at tubes in the middle, or especially like we'll see some of the Baja tubes, stuff will come up, right? And they'll put some sort of like triangle piece here or something, and they'll apply a force here, right? So that tube's in bending in the middle, and we're torquing it, right? So we're torquing it and bending it. So that's not as ideal. If you are going to do a tube like this, you could at least put a tube across to the other side of the frame, basically, to help you use the stiffness of the other side of the frame, or even tie this into a node. Like if this is a node, you could tie these into nodes to help you out on the other side of the frame. But some of the stuff you don't have cross members. One, because you might not want it to be too heavy, and two, you don't want it to be interfering with the driver's legs, right? So there's some places where a cross tube would add stuff to the driver's legs. So so the most important metric usually for a frame, first thing, is the torsional rigidity of the frame. So like, what number should you pick for the torsional rigidity of the frame? And so that's kind of the case, right, where if you look down the frame, let me just torsional rigidity. What's the best way I can get a picture of torsional rigidity? Just go to Google. So you can imagine the torsional rigidity, right? It's basically if you fix these front two, so these are fixed, and fixed. If you apply a force up here, right, and a force down here, how much does this thing rotate, right? And also what's important is the bending. But I think a lot of times you'll notice, like for this, bending is basically if you kept these two straight and you put up on both sides. So this is like rigidity, torsional rigidity, right? And then bending would be if you did both up. So this would be like F and F, and you fix those other sides. This would be like bending. But these two are typically related. As you can tell, I mean, one's just both going up, one's going down. So most people's primary metric is the torsional rigidity. And the question might be, what torsional rigidity should I be testing my chassis for? And so kind of the question is, well, what issues start to arise when you do not have enough torsional rigidity? And so well, the one thing that you spend a lot of time designing is about your load transfer of your front and your rear, right? And in your front and rear, you assume, in this case, we assume that the chassis is rigid, right? So if your chassis is less stiff than your suspension, then all of your calculations you do assuming the chassis is stiff are all kind of wrong. So a lot of times what people do is they say, okay, well, I want kind of this roll, kind of the roll or like rotation of my frame to be like less than 10% of the total roll compared to what I'm getting in my suspension, which typically involves making your torsional rigidity maybe 10 times the roll stiffness of your car, right? And so that's why the roll stiffness number is kind of important. So let's give us a ballpark number for formula. So we said that K of the wheel was equal to 2 pi times omega n squared times the mass of the suspension. So for FSAE, right, maybe omega n is around 2 hertz, and the mass of the suspension is maybe 140. No, let's do 130 pounds force divided by 32.2 feet per second squared. And for Baja, you're probably more in the range of 1 hertz, and your sprung mass is maybe on the order of 100 pounds force divided by 32.2 feet per second squared. Let's do a quick calculation. So I'm going to do 2 times 3.14 times 1 for Baja squared times 100 divided by 32.2. So this Baja, I get kW as 122. This is going to be pounds force per foot, right? And then for formula, I'll get 2 times 3.14 times 2 hertz squared times 130 divided by 32.2. That's for formula. I get K wheel, and if someone wants to check, you can feel free to check me. That'd be good. 637 pounds force per foot. Right, so Baja formula is both higher on the natural frequency and the sprung mass. So theirs is quite a bit higher, especially since this term is squared. So it should be like 4 times higher, right? And then we said, okay, well, the roll stiffness in both of these cases, our roll stiffness, K phi, is 1/2 times our wheel stiffness times our track width squared. So our K phi for formula, right, is 1/2 times 637 pounds force per foot times the track width is I don't know, 4 feet. Squared. So your K phi is 0.5 times 637 times 16 roughly. So this is 5,096 pounds force feet per radian. Or if we multiply this by, we can multiply this by 2 pi radian for every 180 degrees. We can go times 2 times 3.14 divided by 360 degrees. It's about 88, let's see here, 88 pounds force feet per degree. So I'll check those numbers for me. Keep in mind, this isn't even the worst case scenario because you might be a little stiffer in the rear even than this. All right, so let's check for Baja. So for Baja, the K wheel is 122 pounds. So K phi for Baja is about 1/2 times 122 pounds force per foot times your track width is about the same. It's also about 4 feet squared. So yours is 0.5 times 122 times 16, which is 976 pounds force foot per radian. Or we times this by 3.14 divided by 180. You have about 17 pound force foot per degree of rotation. So for your frame, if you want to, I would say you want to be at least 10, maybe not 20 times stiffer in your frame than and you can look at these as springs in series if you want. So if you're actually on the frame, folks. So maybe you want this to be 10 to 20 times. So let's look at 15. So for formula, it's 88 times 15. You might want like 1,300. So K of the frame for formula, you want somewhere in the range of, want to round up to 1,500 pounds force foot per degree, so that your frame is much stiffer than your suspension. And for Baja, it was 17 times 15. So for Baja, maybe K frame is equal to maybe around 300. And you might be lucky in that when you design for the when you design to meet the rules, you might pass some of these already. But you should definitely be testing your frame's rigidity. So let's talk about testing our frame's rigidity a little bit here. So let's go into everyone's favorite software.
And so the right way is like when you do this, then you go back and redo or like recheck your suspension calcs to get it more accurately.
Well, we basically assumed this was 100% rigid, right? But in essence, it's kind of like springs in series, right? So this is deflecting and your suspension is deflecting. So yeah, so I think if you just do this assuming trying to make this almost negligible, maybe less than 5-10%, somewhere in that range, probably most of your suspension design is probably okay. If you really want to impress the judges, if you said, hey, I designed my suspension knowing calculating the deflections associated with my frame, I mean, that would be impressive. Okay, so I mean, the first thing you should do is you should create the cross section of your tubing, and then you'll have to put it in a folder. So for example, you'll have to go and put it in your programs files, the Solidworks Corp, Solidworks language, English, your weldment profiles. So I put in some custom ones. So I put in like Baja is basically. I had trouble with, you have to save it as a special type of file and you need to put in two. So you'll have ANSI inch and ISO here. I had to put two files in, custom, and then I had to put in Baja and then put in this. And I put that in here. And then I had to like mess around with the security settings and stuff, but eventually I got it to work. I don't know. Is there some trick to this, Leo, or someone who does these a lot?
I think.
I mean, I got Andy to help me, but then I tried doing it myself and somehow made it to work after so many trials. But I don't know exactly the proper way to do it.
Yeah, that was me
He
too.
did it for me. Or he knew it.
What'd you say, Juan? Did you have something systematic about why it doesn't work at first sometimes?
It usually asks for like administer like approval or something like that.
Yeah.
So what we kind of figured out a way to do it is we uploaded like exactly how you had that Baja file.
Yeah.
We put it on our desktop first, and then we uploaded all of our profiles onto that folder, and then manually copy pasted onto the
that special location of the
where it says ISO and the Weldments thing.
Yeah.
I don't know why if you do it in that order it works, but it works.
So I ran into that issue, but so let's do some 3D sketching. So I think under sketch there's 3D sketching. I actually don't know that much about 3D sketching, but at least I know when you click on it, you can do like X, Y, or you can tab through and you can sketch on the YZ, or you can sketch on this plane. So let's first just sketch the base of our frame. So I don't know, I think let's just make our frame like 48 inches long. Actually, no, let's make this 60. Let's make it like roughly your wheelbase, and then maybe like, it's like 2 feet in this direction.
A lot.
Fine. Maybe it's, what is it close to, Leo? The front portion of it. Is it 18?
Yeah, 18.
So this is kind of the base of our frame. And then we'll have a front tab. We'll do the front portion of it here and this portion of it here. So this, we'll make it 18 by 18, I guess, just for simplicity. Make this 18. Make this 18. Okay, and then I just need to connect the top for now. So let's connect the top. We'll drive a boat at first, and then let's put in like a little fake, like kind of suspension arms. So I'm just putting in like kind of fake suspension arms, like just so that when we apply the loads, they're kind of distributed correctly into the frame. So I'll put these. So if this is 18 and our track width is roughly 4 feet, so that's,
wasn't it?
15 inches or so.
Oh, 50.
And then this one is going to be, so Pythagorean theorem, so this is going to be 9, so that's half the 18 squared, so 9 squared minus, no, they're going to add, plus 15 squared raised to the 0.5. If I didn't break it. That didn't seem to work. Equals, maybe I didn't put the equal sign. Equals 81 plus 15 squared raised to the 0.5. There it goes. I just put the equal sign. Okay, and I should have been making everything kind of equal to other stuff like we did in the steering, right? I should just make this equal to this so I can change like one of them, right? And not have to change them all. This one. This. I like to make them all reference back to the original one. I don't like to link them just because sometimes if I delete this arm, then it's like everything goes haywire. So I know I like to know, oops, I just did that one. This dimension is going to be equal to this dimension. Equal to this dimension. That's kind of cool. If you click on it, it doesn't like link it. This one is equal to this dimension, but it'll just bring in the value, and the distance out of this triangle is here. I'll do it again, equals here. All right, so we kind of have the base of our frame here. All right, so here's kind of the boat of our frame. And then we need to add the tubing. So we'll add, say this is a structural member, custom Baja. So you select the one you want, and then we're gonna put in groups. So I'm gonna, you kind of usually do like circles, right? Because this will tell you how the things are mitered together. So if I do something stupid, you guys have done this more than I have, just tell me. So those are those groups, and then I don't think it'll let me choose that one. Oh, it does. That's nice. I don't think it'll let me choose this one though. So new group, these three. I think that is probably kind of dumb to do it like this. It's probably gonna like make the joints weird, but honestly, this doesn't really matter all that much for the test we're gonna run. It's not actually gonna consider the way it's mitered together. So if we look in, like, probably see some tubes are a little, oh, they're actually not bad. All right, so we got our frame, and the next we kind of care about is what's the torsional rigidity of our frame, right? So let's go into the simulation. Let's do a new study. We want to do a static study. We could look at the frequencies of our frame. That would be an interesting, have someone come and give an advanced topic about. The first thing I'm going to do is I have to apply a material. So let's say we're using chromoly, so 4130. Yield strength 66. This one thinks it's a little higher. What does it think first? They seem like they're pretty close to me. Tensile strength changed a little bit. Whoa, this one's got a really high tensile strength. I'm applying this material to all of them. Hopefully it did it. So right now you can see you have weldments. It has nodes basically. So what we can do is we can apply some fixtures. So what we can do is we can fix this node, and we can fix this node, right? And then let's go to our external loads and let's apply a force. So we're going to apply it at a joint, apply it at this joint, and I need to pull in my reference frames. So maybe my right frame will be my reference frame is my right frame. And I want English. I want this one for, I don't know. It doesn't really matter what you put in here, to be honest with you, because it's linear, so you can put in anything. So we'll do 100 here, and then I'm going to do another force. I could probably have been smarter and just applied a torque, but I don't know. I'm trying to make it simulate kind of roughly how the loads would go in for kind of rolling our chassis. English, 100 pounds force. Right. So right now you're going to see it's going to do a beam mesh. So honestly, a beam mesh is what you guys should be using a lot for these, like anything that's long and slender. It's much harder for you to make a mistake because it's much easier to mesh. It basically meshes by itself, right? As opposed to doing like shells or 3D elements and that sort of thing, where there's like a million things that can go wrong. So like this should be kind of your baseline. That's obviously, that's a bending test though. Right, we don't want to go both up. We want to reverse this direction. There we go. All right, and so let's run this study. So that looks right to me. So that's the stress. So let's look at our frame. So so we're gonna look at we're gonna look at the max stress. We'll look at it in KSI. We'll look at the deflection in inches. And then we will look at the rotation in degrees. Now let's just do in radians and then rotation in degrees in each step. And so this was for our, so when you're running FEA, you should kind of have a log of all the stuff you're doing. So we're going to insert. And so the moment that we're using right now, so the moment that we're doing right now is we're doing equals to 2 times 100 pounds force times, we're doing it at, what was the track width that I made it? 4 feet?
48, yep.
Yeah, so this is times 2 feet because each force is acting. So 400 moment, and this is the moment we're applying to our frame in foot pounds force. And this was for our open frame. Open frame. Okay, so let's go look at our results. So our max stress. Oh no. Hey Juan, how do I change this? Change the units of this?
The units of the
chart.
Right there. Yeah. PSI. Do you want to get it out of out of like to the power of 4?
No, that's fine. So this is 16 KSI, right? So max stress here is 16, right? The deflection, so I'm gonna look at the deflection in the displacement chart. And this is in millimeters, of course. Oh, so it's deflecting by an inch all the way out here, but this is all green. So so I can probably probe this, right? If I right click, probe it. Let's probe this location. So this is 0.4 inches. So 0.4. So the rotation in radians is going to be equal to, this is going to be this value divided by 9, because that's the R, right? And so rotation in degrees is equal to this times pi divided by 180. No, it's going to be the opposite. Last time our unit was per radian, so now we have to do the opposite. So it rotates 2 degrees. So here our rotational stiffness, or torsional rigidity, is going to be equal to our moment divided by this. 157, that's not good. This is pound force foot divided by degree. And what we wanted, what we were shooting for here, right, was, it was on the order of 1,000, right, was what we were shooting for, at least for sorry, for, oh no. Okay. At least for like formula, we wanted like 1500 or something like that, right? And for Baja, we wanted at least like three, at least it was like 600. Is this right? 0.4 inches. 0.4 divided by 9 was the radius. Okay, I think that's right. I'm surprised how stiff the frame is already. I mean, I guess it is all primary tubing. And so keep in mind, so if you had the actual suspension members in, I would probably look at the deflection out here, right? But because these aren't the real suspension members, I'm looking at the rotation of just the frame. And that's probably more specifically what the torsional rigidity refers to is of the frame. But honestly, what we care about is kind of the torsional rigidity of our whole car. So, okay, so let's go back into our model. Let's see what happens. So like, I mean, the first thing I would do, right, is probably add some crosses here and here, right? So like, the first thing I'd do to stiffen this thing up would be to go from here down to here and probably here down to here, right? I'll just add these as a new group. This one, this one. You also need to be a new group, really? It's not play nice. Okay, so we're reconstructing our beams, right? So this is a 1D mesh. Juan, do you know how, does it somewhere tell you like, oh, okay, the type of mesh? Oh yeah, here you go, mesh type beam, right? There you go. So you can tell this is a different color. That's because I need to come back here to my part and I need to apply the material to all the bodies again. So apply, close, and I got this gray. Let's run this study again. Okay. So the max stress now has dropped to about, I don't know, this orange color. So maybe about one, so let's see, let's just do a probe. So probe like this point right here. So about 12. So it dropped quite a bit with just those members. So long triangulation. So I dropped to 12, which is pretty good. And then if we look at our displacement, I don't know what deals with that one. So we can now do again a probe. Probe right here in the middle of this spot again. So this is 0.22. So 0.22. This one we need to F4 the blue one. So we've already doubled the rigidity now. So let's see, let's keep going on this. So back into our model. So I'm not happy with my frame yet, so I'm still trying to get it more and more rigid. So I'm thinking, okay, well maybe I'll add across the bottom of the frame, I can add a member here. I mean, if you want it even stronger, you might be able to do an up and do a double triangulation. So I'll add this one. And let's see what happens. I'm saying, well, maybe I'll This is the driver's back, so I can add one there. Maybe this is the driver's feet, so I can add one here without paying a penalty. But the driver still needs to get in and out, so I can't add one to the top. All right. So let's add, and you can see I'm adding triangulation, right? Like, there's no point of adding, like, don't add, the square faces are bad. You want to get rid of square faces because the square faces, like this top bar can go left, right? And these will just rotate down. So nothing has to be in like a square, can kind of parallelogram, right? Without having to change lengths, which means it's all in bending. So by having triangles, it has to be in tension and compression. So we're gonna edit this feature, right? I'm gonna add a new group. I'm gonna add this one. I'm gonna add this one. That one is a new group. Okay, so we're gonna go back into our static study. The beams. We need to apply material to these new bodies. That's good. Rerun the study. All right, so the max stress is now, let's probe. About 1.5. That's interesting. Thinks it's about 15. I'm a little surprised that the bending stress went up in this tube. It makes sense. It's the only one not triangulated. I guess this tube now is like carrying. This one's, everything else is really rigid except for like this square up here. So it's really deforming that square. So that's interesting. So that didn't really help much with making it stronger. But let's see here. Let's probe the displacement. 0.25 roughly. So it didn't help much with the deflection either, actually. 0.25. So this is more triangulation. And so max stress was about 15. So it might go down slightly. Let's see here.
Chris, the entire top of the chassis doesn't have to be open like that, though, does it?
No, we could close off some of it. That'll probably help. Let's try that.
I don't know about the 50% mark.
All right, let's try that.
Or a little better. Maybe go 55 or 60% mark.
So we'll go about 60. We'll come here to about here. And then we'll go here. So out of that, and then we might have to change our plane. So we'll click this. I like it better if I go here. Right. I mean, it would love to have a cross member from here down to here. That would really make this thing happy. But let's try with this to start. And then let's add this. So add this one. Make a new group. This one. right? So we might even segment these half off too at some point. So and let's apply material to all bodies, apply, close. Interesting. So if we probe here, so that's about 12. So that's a little happier on that. And then let's look at the max displacement. And let's probe. Let's put it here. So this is 0.005, so that looks a lot better. So 0.05. So that gets us close. So this is front, top, and closed, right? And then, so you can see, I mean, and you might also too, you might make kind of another square in here, right? And you might try and, so you'll see actually old cars, they'll have like they'll have a special piece of material in here. Let me pull up that's right, pull a picture up of one. So you see this? So you see where they have an open square, they can't do a triangle. They would use these incredibly stiff hold out patterns here and here. Look at it again. So they'd use those because they could not do a triangulation around the frame. Oh, there you go. See? So no stiffness, and that's against the going in parallelogram. This is idea, but this, if you can't put something across, sometimes you have to make a square in this frame, super stiff, right? And that's why they put basically bulkheads, right? So that's where you have special areas that have that stiffness, because you can't get this tube across here because someone's feet have to go, right? So let's so you know, for example, like let's say if you didn't care about the person, how good could you get this thing, right? So I think the ideal thing would be to take a tube and go here up to here, which you obviously can't do because the driver is going to sit here. But let's just look how much better it could get if you could get some material and tension and compression.
Your tubes that went from 4 on a diagonal from the back to the front, you could tie into those on a diagonal. That went right through the car though. It ain't gonna work.
No, this one ain't gonna work. But just for
Kicks.
For shits and giggles. I mean, you might do one up top and then one down to here too as well. Actually, I'm gonna do that. I mean, we can probe here. So this is slightly less, but let's go back into my model. Sketch. You should write all this down, but we're running out of time. Because our top is weak, I'm actually gonna tie in the top. I think we'll get more bang for our buck. Well, didn't like that. I messed with one of my other groups, I think, basically, but let's see if it can still run the mesh. I might not care about the weldments here in the mesh. Okay, so we'll run the study. So this is good. So we probe it now. Right, so now we're only at 7. So this is with full diagonal. So we're at 7. So we're much better. And then in terms of the displacement, we'll probe it. So here we're at 0.0038. 0.038 actually. So now we're at the 1650, right? So now we're up, I think, in a place where we're pretty happy. So now, if we get something like this, we'd be pretty happy. Obviously, it was not super easy. It was not super easy to do though, right? So you can see, and we even have one too that's not really physical, but we might want to create a structure in here that's really stiff. So you might even add some downsides and shrink up these triangles to see what happens. But you should see, I think that's roughly the process I would go through with the, roughly the process that I would go to. Like, I think some strong bulkheads would help. The process that I would go through. So I guess the last thing I would talk about, the frame, so we got our 1500 there at the end, but we would have to do a lot more, is how would I kind of go about designing the car, basically. And so, the first thing is you got to read the rules, right? Right? I think we need to know, like, what can and not do, right? So you read the rules. So you also, I would say, along with that, you should know what the competition is like, right? You need to know what the track is like for all the events. How things are tested, right? Knowing all these details is really, shoot, for Baja, we care about how do you line up in the morning for an event. We know on the first day of all the dynamic events that the hill climb gets eaten up. And so you need to get in line for hill climb first for a fresh hill. So we, on dynamic day, we will immediately be the first ones in line to try and go to the hill. And you'll see teams on the acceleration events, for example. I saw Michigan was there. They had someone videotaping different acceleration runs and feeding it back to the captains because the grass was kind of wet early in the day. And they were seeing how wet it was and feeding it back. And they wanted to get it to the point where it was no longer wet in the acceleration event, but it was not, the grass was not eaten up. So they were waiting for these like perfect conditions, right? So but anyways, you need to know what's allowed by the rules and what are they actually testing you on, basically, right? This gives you basically an idea of like the power unit you need, or that you can use, power unit, like engine and the track, right? And which will help you make decisions about your tires, right? So I think Bill and I were talking about this. One of the first things you should start to pick are your tires, basically. And you should be doing some of these simulations to say, like, all right, how much grip do we actually need? Do we need 13-inch tires? Can we get away with 8-inch tires, right? When you see a lot of the best teams going even to 8-inch these days because they can package. I think it's hard to package them. But if you can get your car light enough, you might only need 8-inch tires. And then if you can get them, if you can get your tires lighter, right, you need less grip for the same speeds, right? So especially since they rotate, your tires count as double their weight, right? So you get your tires, right? And then you're starting to think about your track width. You're starting to think about the wheelbase that you're going to want to design your car, right? So once you start at the tires, you start out where are these tires starting to be located? Then 4, you're starting to think about your suspension, right? So you're starting to think about your suspension. You're starting to think about your roll centers, right? You're starting to think about your kingpin inclination, your scrub radius, right? So you're starting to think about your kind of the geometry of your suspension, right? And after that, I think you start to think about the dynamics of your suspension, right? So I think those will both come into play. So you're talking about suspension. 5, I think you're starting to think about your drivetrain. I mean, this could go at the same time after your wheelbase and track width. You're thinking about your drivetrain, thinking about your gear ratios, how you're getting your power out to the wheels, right? Once you know your suspension, you can know if you can use U joints or CV joints, right? You start about the drivetrain, and then you know, you're probably at the same time you're thinking about steering, especially with the suspension. So we should kind of call these like maybe like 4A, 4C. These are all kind of happening together, right? Or you're kind of thinking about all these and you're kind of iterating, talking to each other, because steering affects the suspension and vice versa. Same with suspension and drivetrain, they're affecting each other. And kind of 4D probably is your chassis, right? And your chassis basically is looking at how can it support all these other systems and keep them stiff, right? So if we look at, so then you're thinking about your chassis, I think last, and you're thinking about driver connections and stuff. I mean, it shouldn't, you know, it shouldn't be neglected, but I think that's kind of the order at which I'd approach this problem and the process I'd take, right? And so I want to show. So like, I don't know. So let's look at some kind of examples. So I put all these in here. So we'll start with like formula, right? So we talked a little bit about like our last year's car, right? Like we talked about, so you see how it's not tied into the node here, and it's bending this, putting this tube in torsion, and this mount is in bending, right? And all these mounts ideally would come down here lower to the node if you could, right? That's how you would design it. All right, I think our front was better. It's hard to see here. Maybe we can see it better. Ooh, I don't have a picture. I gotta get a picture of the front with the nose cone off. This one? Yeah, you can kind of see it here. So I think they did a good job of putting the mounts close to nose, but there's a lot of tubes in the front here. Remind me to get some more pictures of the front. Or let's look at like Baja. Let's look at this year's car. So some things I think you could like, so I mean, me and Juan have talked about strategies for this stuff a lot. And so, but some just things to think about, right, is like your shocks mount into the middle of these tubes, right? And these tubes, this helps by having something go across a little bit, kind of hold the torsion in both tubes basically, but it's in bending and torsion, right? And you also see like this bottom lower control arm is connected like halfway through this tube and not up at this front node where it probably should be connected, right? And let's see if we have some, trust I don't have 2020 pictures on here. Yeah, let's look at like here. So like again, like if you look at the rear, right, like this is pretty close to a node, which is good. This is kind of in the middle. That's not so good, but it's just the top link. The top link doesn't handle a lot of force. But the shock, right, this shock is right in the middle of this long tube, right? And the tube is bent here. Like this is probably not a good design. I probably wouldn't bend the tube where I mount a shock to it. And it's going across, right? Like ideally this tube, the shock should be mounted like right up here into this node right here. Something super rigid. But yeah, I think with that, so that's the end of kind of all the lectures I was thinking about giving. I'll probably, you know, I'm guessing folks will feel free to request to talk about something again or to look into something more specific.